relations. Then there is a theorem. Adiabatic connection. Hybrid functionals. And so on. Okay, so we begin with, if you do a coordinate scale, right? So then how do these functionals as functions of n change? And this becomes a mathematical relationship which should be satisfied when you construct functionals. So for example, if I take the kinetic energy, right, which is equal to psi, the kinetic energy operator psi, and if I change the coordinate, do the coordinate scaling, that means if I let r go to some alpha r, I know in the terms of wave functions how do things change. For example, if I do psi r2 psi r alpha, right, and I still want that, so define this, target some constant and define this as psi alpha r, that is scaling psi r. Then for proper normalization, I should have integration mod psi alpha r meaning all r1, r2, r3 and all that, mod square dr. This should remain 1. And this implies that the scale psi r alpha will be equal to 1 over alpha raised to 3n by 2 psi That's how it should go. That you can check right away that if I do mod psi alpha squared, it will be equal to alpha raised to 3n psi alpha r mod squared, and if I integrate it over r, meaning for 3n variables, then becomes integral psi z mod square dz, where z is alpha r. Okay, so this is how it scales. In the same manner, the density, define n alpha r, this you can see right away, is therefore which is equal to modulus of this is going to be alpha raised to 3 and alpha r. Alright? Now we do it in terms of n. Well, I'm not using rho. If I take the expectation value T rho and want to calculate T rho alpha, right? What would this be? This will be equal to psi alpha T operator psi alpha, which is nothing but alpha raised to 3n integration psi alpha r star. T operator is 1 over r square, so I can write this as alpha square and T in terms of alpha r sine alpha r dr. Right? And this, I can take alpha r to be z. So T rho alpha will go as alpha square dr. Right, so if you construct a kinetic energy functional, you should be able to check right away that this is how it's going to scale. And where E rho alpha is defined as alpha cubed. Rho alpha. Is that okay? And similarly, you can show that the expectation value of VE or as a function of rho alpha is going to be alpha VE. Leave it for you to check. Okay? Alright. So these are some scaling relationships which we will use a little later. Now we come to Villiers theorem in DFT. If I am talking about Villiers theorem, what I should do? What does Villiers theorem do? It relates kinetic energy with the potential derivatives. And then we can also derive some relationships where the energy functional is related to the derivative of the exchange correlation energy potential. Exchange correlation potential. So, how do we derive Villiers theorem? The way Villiers theorem is derived is you write the expectation value of operator R naught del commutated with H and write its expectation value. Right, and these are, this you can relate to R naught P, and it's a stationary state, so this is going to be 0. Okay? And when you work it out, so this is Ri, partial I, commutated with H, expectation value is 0, and you work it out, you get 2, expectation value of T is equal to out to 3, will come out to be is equal to expectation value of R not del of quickly check this. So if I take V equals 1 over R dot del V comes out to be minus 1 over R square. So we get 2T is equal to minus V, and you get the right answer. So that's what it is. Okay? So I have 2T is equal to So in the regular theory, this is going to be equal to R dot del acting on V external plus VE psi. Right? This will come out to be integration. Let's write the second term first. If you take R dot VEE, I just did it right here. VEE also has this behavior 1 over R, right? So R dot del will come out to be minus VEE expectation value. Because VEE is Coulombic. So del VEE is going to be minus 1 over R square, and then you do R for that, you get that. Okay? I'll leave it as an exercise for you. You'll have to do one manipulation because VE has both R and R prime. So one small manipulation will have to be done. And plus integration R dot del V external R rho R dr. So the relationship you get is that 2 times expectation value of t is equal to minus VEE plus integration R dot del V external R rho R dr. Now in DFT, what you do is you write E rho as some F rho, which is the expectation value of VE with respect to, so I plus integration V external R rho R dr, and this gives you the equation mu, which is a constant equals del F over del rho plus V external R. Now we are going to relate, get rid of the external R, so what I am going to do is multiply by R dot del times rho R and integrate over dr on both sides. If I take the gradient of this, that's going to come out to be 0. So I am going to get 0 equals partial F, partial rho R dot del, integration rho R dr, plus integration R dot del V external R rho R dr. Is that okay? So this is my equation number 2. Equation number 1 is right here. 2 T expectation value is equal to minus F rho plus integration R dot del V external R rho R dr. Equation number 1. Subtract 1 from 2 or 2 from 1. You get 2t is equal to minus F rho minus integration R dot del F del rho dr. this was VE, yes. So I get VE. Bring that VE to the left hand side. T plus VE is F rho, so you get T rho plus F rho is equal to minus integration R dot del acting on del F del rho R here. Are you with me on this? Yes? Okay, so this is one relationship. Several. So one of the relationships that relates without any reference to external potential for any given density, T rho plus F rho should be equal to this. Only thing is that you assume that VEE is the electron interaction. The interaction is coulombic. External potential could be anything. Is that okay? Alright. Another relationship. Now related to the exchange correlation. So that's number one. Relationship number two. We start from this. I have 2T is equal to minus VEE plus integration R dot del V external R rho R here. Take the Kohn-Sham system. In the Kohn-Sham system, I'm going to have 2 Ts equal to, what is the interaction in Kohn-Sham system? 0. There is no interaction. The only thing is this. So I'm going to get integration R dot del V Kohn-Sham, which is nothing but V external plus V Hartree plus V exchange correlation rho R dr. Is that okay? Are you with me on this? Okay. Let's go further. And subtract. If I subtract, what do I get? I get 2 P minus problem is 2T minus PS is equal to, subtracting this from this. So V external term will go away, right? And I'm going to get minus VE minus integral R dot del VH on rho R dr minus integral R dot del VXCR rho R. dr. Alright? Okay. Now, VEE is nothing but minus, what is VEE? It gives you E Hartree rho minus EXC quantum mechanical rho. Right? This is the expectation value with respect to the full wave function. Minus again with some manipulation. You can show that this term inside the integral is minus EH rho. So this comes out to be plus EH rho. So what I'm using is this thing minus EH rho minus integral R dot grad VXC R rho here. This thing cancels. And you bring this to this side. This is nothing but 2 PC, the interacting kinetic energy. You bring the other thing to the side, you get TC plus EXC quantum mechanical, and that's EXC DFT is equal to minus integral R dot grad VXC R rho R here. That's another linear relationship. Given a functional EXC DFT, if you know TC, the potential, they should satisfy this. Okay. One thing that you'll notice here, because there's an R dot, this term is origin dependent. If I change the origin, an extra term comes. So if you really want to use it properly in atoms and all that, there is no problem. Other places you have to make some adjustments. Okay, but this is a good relation. Any questions so far? This is all manipulations. Okay, so that's the other relationship. Now, I'll go further. We can split it further. We can split it further to exchange part. And after I do adiabatic connection, I'll be able to justify it. And that will be that EX DFT rho is equal to minus integral R dot del Vx alone on rho R here. Okay, that means this is equal to integration R dot del delta Ex over delta rho R rho R here. This also works out well if you are calculating it, do a long calculation, check, get the functional derivative, it should satisfy this. Okay, so you can always do it, check on your calculation. And the TC part goes to correlation, so you get TC is equal to minus TC is equal to TC DFT obviously rho plus integration R dot del acting on V C rho here. Any questions so far? Notice that all these relationships only assume that the interaction, right? So these are valid for interaction. VE R prime equals 1 over R minus R prime, and independent of U's and R. Is that okay? Any questions on this?
So I'm not following this section where 2 is equal to minus E, and then the middle section.
Where?
Middle section.
This one, huh?
So the last step we have written
Yes. T minus T S is TC.
that is fine.
Yes.
Later in the last term we have TC plus.
Okay, so 2 TCs there, 1 TC is left. To the other TC I have added this. Right, so this is I have used that EXC PFT is psi VEE psi minus E Hartree rho plus EC. Alright? Okay. Any other question? Alright. So there's the other relationship. Now we will come to this again, and I will that relationship. So now we will do adiabatic correction. In the adiabatic connection, what one says, suppose we change the potential, the electron-electron interaction potential in such a manner that it goes from being 0 to full, right? Then we do calculate, we define the energy in terms of n bigger. So using Helmholtz-Feynman theorem. It says that if a Hamiltonian is h plus lambda v, sum h 0, right? Then the energy E d lambda is given as psi calculated for this Hamiltonian dh by d lambda by lambda. And therefore, E minus E0 can be calculated as E1 as integral psi lambda dh by d lambda, in this case whatever it is, V psi lambda d lambda. That's the Helmholtz-Feynman theorem. This we learned in quantum mechanics. Now let's do this V lambda business in a very, very particular way. And the way we are going to do it is we take our Hamiltonian, which is the kinetic energy, plus make VET, change it by a factor of lambda. Now it need not be in this form. I could also take it like e raised to minus lambda r over r form. So that when lambda is, in this case when lambda is 0, there is no interaction. When lambda is infinity, or in this case when lambda is 0, there is Coulombic interaction. In this case when lambda is 1, then it's full interaction. In this case, when lambda is infinity is 0. So we just go with the upper one. Yes?
Lambda is used to graph the quotients with the
Yes. And correspondingly, I also change the external lambda such that so this I call as lambda rho r remains unchanged. Right, is the idea clear? So before we do that, you may ask, can you even find this? Right? Lambda is between 0 and 1. Well, right now that question is not arising, but yes you can. And that also provides a way of checking your functions. But right now let's just do, so I'm going to do E for the full lambda equal to 1 minus E0 is going to be integration 0 to 1 d by d lambda is going to be here VEE psi lambda VEE psi lambda d lambda plus integration d by d lambda V external lambda rho r d lambda. Notice that density remains the same, so this is rho r. It's a multiplicative thing. Right? And this is nothing but integration psi lambda VE psi lambda d lambda integration 0 to 1 plus integration V1 r rho r minus integration E0 r rho r. Now, when lambda equals 1, then the potential becomes V external 1 and this is a true system. And when lambda equals 0, V external becomes V external 0, which is the no interaction, full potential, same density. So this is a Kohn-Sham system. Alright? And what is E1? E1 is T rho, or I can now write Ts rho plus integration V external 1 true system R rho r dr plus E R2 rho plus E exchange coefficient. And what is E0? E0 is the energy of the Kohn-Sham system, which is going to be Ts rho plus integration V external 0 rho r dr. Right? So E1 minus E0 is going to be nothing but Ts rho cancels. Right? This will cancel with this first term, this will cancel with the second term. Right? So you get on the left hand side, you know that EH rho plus EXC rho equals integration. Since rho remains the same, I can write this as 0 to 1 psi VEE psi lambda minus E rho d lambda plus E. And this cancels. So you define your EXC rho. equal to integration 0 to 1 psi lambda VEE psi lambda d lambda minus 0. If you could calculate for each lambda psi, this is what is going to be your answer. Okay? So this is the adiabatic connection formula, and through this you can also derive rho xc dft, which will be in terms of the second order density matrix corresponding to psi lambda integrated over lambda. Okay, this has given rise to the first hybrid functional. So you can take, if I take lambda equals 0, psi lambda is nothing but pi Slater determinant of Kohn-Sham order. Right, because the non-interacting system. Right, lambda equals 0, the Hamiltonian is minus 1/2 delta square sum over I plus V Kohn-Sham R. So psi 0, VE psi 0. When I calculate the expectation value of VE with respect to psi 0, it's nothing but E Hartree plus E exchange goes pi I Kohn-Sham. Is that okay? And therefore, this is going to be EXE rho for lambda equals 0, it's going to be EX. Expression is Hartree-Fock expression, but the orbitals are Kohn-Sham. And now I can say that EXE rho approximate is roughly equal to, take the average, 1/2 EX Hartree-Fock, EX lambda equals 0 plus 1/2 EX lambda equals 1 EX. Lambda equals 0 and E is exchange. So this is half E Hartree-Fock calculated in pi Kohn-Sham plus 1/2 EXE density function approximation. That's Becky's half-half hybrid formula. Okay, this is the motivation. Alright, and after this there was a flurry of activities as to how to mix. Now, Janita in her sota was saying that the idea of mixing Hartree-Fock is that you get the correct band gap. But it's not just that, it's the mathematical formulation to Adiabatic. Yeah. Is that okay? Alright. And after that there have been many, whether it should be 1/3, 2/3 here, or mix and all that, I'll leave, but that's the basic idea. Now, how to study functionals of DFA. Adiabatic. There have been a lot of studies for this, right? And also it is interesting to see how, as you change lambda, if I change electron-electron interaction, how does the potential external potential change? You keep the density the same. So what you're doing is, EP, the density, same, and create an external potential corresponding to lambda VE.
Yes, the conceptual point here.
Is that?
The conceptual point is
Yes.
In conventional television, when we go from non-interactive to interactive system,
Yes.
so we essentially, let's say, we argue for Fermi liquid. There is a adiabatic continuity. There is that the non-interactive states can be tuned in the sense of adiabatic continuation to interactive.
Yes.
But then there are cases where it breaks down. So in strongly interactive Fermi breaks down because we no longer have Fermi description. No possibility.
Okay.
So I'm just wondering here, because the Bonchamp always guarantees that there is indeed a function.
Bonchamp always says that Bonchamp assumes that this density can be written in a non-interacting system.
Yeah, so when we do this adiabatic transformation, is it always guaranteed that the adiabatic connection remains?
Yes. Yes.
Between the Bonchamp and the
The Bonchamp interacting with the density will be the same. Always changing the interaction from 0 to 1. And we already said that it exists for each interaction.
Perhaps there is some difference between the standard way of, because can I, for example, describe a non-Fermi liquidity? Suppose I could. In a conventional non-interacting problem to the interactive.
If you look at Fermi liquid is also an approximation, right, to the real system.
Yeah, that is why the adiabatic connectivity is necessary, because you should always be able to continue to the non-interacting problem.
Yes.
So I'm just asking here in the
Yes. So whatever cases we've studied by doing this, we could do it.
okay. At least in the conventional until
Yes.
you said very specific.
And there is there's one paper long ago which I'm not upon, is where it is shown that this always exists.
I see.
So that is shown by the
Okay.
late. So for this, what we do is again, given a density rho r, solve the inverse problem. Alright? So I can calculate E for a given P and subtract this V lambda rho r dr and EV I will calculate for lambda and maximize. That's one straight away way of doing it. And you can find V lambda. You can also do another way, you can construct sum with the constraint that psi lambda will give rho, and we try it for electron systems. And what it does, once you have done this, right, what it does is it gives you a nice way of checking your functionals. If I have a functional, and if I could calculate what the integrand for the functional should be, I can always calculate the exact one for a given density. And for the same density, I can calculate my functional, then integrand and compare it. And if it matches all over the place, that means your functional is decent. So it gives you another way of checking a functional. Rather than calculating energies and things like those, it gives you another way of checking the function. I'll come to that in a minute. But right now, I just want to focus on adiabatic connection. Okay. So another hybrid function, which is known as the range separated functions. And the idea is as follows. If you have a system and we have shown that far away the potential VXC goes as minus 1 over R as R tends to infinity. And this is not satisfied by the functionals, LDA and things like those that we use. Okay? And so the idea is that write 1 over R as a short range part. This one can be done into error function plus a long range part. Okay? So there is some error function involved and we can do it through that. So 1 over R, there is some function short range, which is a function of, let's say, lambda plus f long range, a function of lambda. And then you write the exchange correlation functional as this, you treat as EXC or EX short range, and you treat this in density function approximation. Remember, my final aim is to get 1 over R behavior correct. So for that, what I'll do is I'll treat the long range part correctly. RT4 gives you minus 1 over R. So plus E exchange long range RT4 plus E correlation DFT approximation.
Sir, we want 1 by r long range to be correct.
Yes.
So, what is the problem?
Problem is that the functionals like LDA or GEA or GGA do not give you that part correctly.
What exactly do you mean by not correct?
Okay, so suppose I take EX LDA, right? And this is rho raised to 4/3. Delta EX, delta rho is rho raised to 1/3. And for exponentially decaying, density is equal to minus some power R, which is not minus 1 over R. Decays much faster. Right? And I want that correct. Whereas in Hartree form, is the potential due to the Fermi hole, which is one charge, to the minus 1 over R. I still don't get your question. Are you satisfied?
Yes.
Okay. So I'm going to write this. Whatever the long range part is, calculate EXC in terms of that, phi I star and all that, plus EXC short range, EX short range, rho plus EX, EC, density function approximation. The only thing this does now is makes the potential orbital dependent. You have delta EXC, delta phi I star is Vx C I. Okay, so in that sense this is generalized Mohn-Sham theorem. And then again you can, now one way to do this, fixing, and this became very popular, what is called the optimal tuning of this parameter lambda. Israel group. And so optimal tuning of lambda by ionization potential. Yeah. So what we will do, all this calculation will be done will be a function of lambda. Sure. Generalized KS problem and calculate E as a function of lambda, E for n electrons as a function of lambda. Calculate En plus 1 as a function of lambda. With this, you also get E max n as a function of lambda. You get E max n plus 1 as a function of lambda. Right? And you can also go to the other way. You can do En minus 1 as a function of lambda. Now by IP theorem, you get epsilon max n should be equal to En minus 1 minus En as the ionization potential for n part of the system. You tune your lambda in such a way that this is satisfied. And then you fix that for that system. Okay, so you're trying to fix an exact property by tuning this lambda. Right, that's one way of doing it. Even if you're doing model potentials, you can, where there's some parameter, you can choose this. So this becomes a nice way of tuning your whatever parameter is in the problem. Alright, so that's the optimal tune. Potential is you take V, XC and dA and make a correction to it brute force so that it goes as minus 1 over R for larger systems, and that is some functional, right? Some X is to some 1/3, or that there's a sine hyperbolic inverse out here, some beta which is fitted, or something like that. Okay? The bottom line is that this gives us minus 1 over R far away. It gives you better gaps. Modified Becky-Johnson is based on, again, those modeling the exchange hole in a certain way, which was done by Becky and Russell. And then they came up with the Becky-Johnson formula. And this was modified by Peter Blahan. And what is the other name? T, something with T? Tran Blahan. Okay? And this gave good gaps. And what do we call your function? I will write it. Give me a name. Let's give it a name. Huh? Isn't that a good name? Nice one. Huh? Good gaps. Okay? Now, so I want to make a comment on this, and particularly in light of there is a paper on archive, very recent paper on archive, and this is going to come out in PRB soon. Okay? What they did, they took Monte Carlo densities for solids. So these are supposedly exact densities which have been inverted, and the gaps formed are smaller than E2. So this is the first time they have shown that if you take real density of a system and calculate the true cone sham corresponding to that system, gaps come out to be small. And when they compared these densities, particularly modified Becky-Johnson densities, with UMC densities, okay, and found that the two are very different. Different, yes. So you can take a functional, get a good gap, but if you get a good gap, the densities are becoming back. If you take the true density, you won't take always a very accurate density, but it has been done only for these two systems. Gaps not are small. So this, I think, is going to start a new study in the direction of how to balance the band gap and density. I mean, this is as latest as I can come to band gap.
Design density driven function.
Huh?
Density driven function.
This is what is it? Yours is a band gap driven function.
So what we do, we model the extend formula using some technique.
Yes.
Now,
So that the gaps come out to be organic. Yeah.
okay, now you do something which will mimic the this quantum density.
Yeah. So but then the gaps will come out to be. So this is going to start a new study. That's what. So this is where I'll stop. Okay. Thank you.